Hydrolysis and the common ion effect are related topics very important to our understanding of acid-base chemistry. First, we need to review the strong acids. If you memorize these few acids, you will be able to tell when an acid is weak. Any acid that is not strong is weak. The same could be said for strong bases. If the base is not a strong base, then it is weak. Notice, they come from two groups, the strong bases. Group 1, all of it, is a strong base, and group 2 forms a strong base with just those three elements. When working with solutions, it was found that some solutions are neutral, some are acidic, and some are basic. Hydrolysis occurs when an ion reacts with water, creating a weak acid or a weak base. If an anion forms a weak acid, then hydroxide ion will result. Notice the example. I've got acetate from some source like sodium acetate. I add water to it. I form undissociated acetic acid and hydroxide ion. Thus, the solution will be basic. If the cation forms a weak base, then the hydrogen ion or hydronium ion results. If I take NH4, like ammonium chloride, say, and this is an ion, it will react with water to form an equilibrium of NH4OH with hydrogen ions left over. So this solution will be acidic. So the key to identifying if hydrolysis occurs is to ask two questions. Is the cation part of a strong base? Is the anion part of a strong acid? If either question is no, then hydrolysis occurs. Here are three examples. To determine it, I look at my questions and I take potassium iodide. Potassium metal is a group 1 element. It forms a strong base. Then I look at the iodide part. Well, iodide is one of the strong acids. So in this case, no hydrolysis occurs and the solution should be neutral. If I look at lithium sulfite, not sulfate, but sulfite, lithium is part of a strong base. Now, sulfite, though, is a weak acid, so then hydrolysis will occur. The sulfite reacts with water to form bisulfite and hydroxide, so this solution will be basic. Then we can look at iron 3-chloride. Iron is not part of a strong base. That's a weak base. Chloride is part of a strong acid. So we know that the iron will react with water to form the ferric hydroxide and acid will result, so our solution will be acidic. Okay, for the common ion effect, if you consider a solution like acetic acid in water and you add some acetate, So I'm going to add acetate, maybe from sodium acetate. We'll put it in the form of sodium acetate. That is going to shift this reaction towards the reactants to the left. More undissociated acid will form. So, the idea of the common ion effect, if you have a solution of a weak electrolyte and an equilibrium exists then, say acetic acid and water, and I add some sodium acetate, I've added the common ion acetate. The sodium ion doesn't have much effect, but the acetate will force the reaction to form more acetic acid. The presence of the common ion must be accounted for in the calculation of pH. If you want to calculate the pH of a solution that is 0.2 molar HF in a 0.1 molar solution of HCl, you start by recognizing that HF is a weak acid. Write the equation down. Find the Ka if you need to. There are tables in the book, in your textbook. There's tables online to find the Ka. And it helps to go ahead and write the Ka expression. Then you start with your ice table. HCl is the strong acid. It's present initially in the solution. So when I write my equation, I'm going to include for the acid component the 0.1 molar from the HCl. Then I add the changes to the table and then calculate the concentrations in terms of the variables at equilibrium. I'm going to make two assumptions. One, that X is much less than 0.2, and two, that X is much less than 0.1. Now, I put those values into my Ka expression, rearrange to solve for X, and I find that X is 1.4 times 10 to the minus 3. But I'm not done yet. What that tells me is that X is the fluoride concentration, which is 1.4 times 10 to the minus 3. The hydronium ion equals 0.1 plus that 1.4 times 10 to the minus 3. But that's really small, so the acid concentration actually comes out to 0.1. I find the pH, that's going to be a 1.00. So, to review, you need to know the strong acids and bases so that you can recognize the weak acids and bases. Hydrolysis will help you understand the buffers in our next topic. And when you calculate common ion equilibria, the concentration of the common ion is an initial concentration.